linear codes, generator matrix, then parity-check matrix, and syndrome-based decoding. Operations of a channel encoder of the NK linear code is a determination of code words for the given information word, determination of check bits, K is the length of information word, and then, based on this word, determination of M check bits. Now, this is the operation of the channel encoder. And this operation is described by the system of linear equations in terms of matrix algebra by either a generator matrix or parity check matrix. And I will present you both approaches. Properties of linear code. The all zero word always exists. A second property, the most important, modular to sum of any two code words give a code word. Based on this property, we may say that any algebraically independent subset of K non-zero code words uniquely defines a code, NK linear code, and such subset consists a code base that can be considered as rows of the so-called generator matrix. Two other 3 and 4 properties I'm not going to discuss in detail, they are obvious. Generator matrix. Generator matrix, let me repeat, code base consists of K code words linearly algebraically independent. This is a generator matrix. G1, Gk, K code words. Rows of this matrix are code words, algebraically independent. To obtain all possible combinations of generator matrix rows, to obtain all code words, matrix G has to be multiplied by the matrix of M equal 2 to the power K rows and K columns that contains all possible information words, including all zero words. So this is a strategy of encoding for generator matrix, for the given generator matrix. We multiply this generator matrix by information word to obtain a code word. If an identity matrix appears at the left side of matrix G, like here, then information bits are located at the left side of the code word, and such form is called the systematic one, and the obtained code a systematic code. A submatrix P, this submatrix, K rows, M columns, is called a parity-check matrix. This is an exemplary generator matrix, code 5-3, code word length 5, 3 information bits, 3 rows, 3 words, algebraically independent. Then to obtain all code words, we have to multiply all information words by this matrix. For example, this information word, when multiplied by this matrix, will give this code word. The multiplication is the same as multiplication for regular matrices. The only difference is that addition is modulo to addition. All code words are presented here for this code described by this generator matrix. As we can see, rows of this generator matrix are code words 4, 2, and 1. These are information bits, and these are parity check bits. The minimum distance of this code is the minimum weight of code words, which is 2. For this, for W2 is 2, and also for W5 is 2, which means that the minimum distance of this code is 2. This code enables detection of single errors, and that's it. Other subsets of K equal 3 algebraically independent code words can be selected other than this subset to create the so-called non-systematic code. For example, for this generator matrix of systematic code, we may add G1 and G3, we may leave G2 as it is, and we may add G2 and G3 to obtain other code base, a set of code words algebraically independent, but this code base, this generator matrix, is a non-systematic one. These two codes, the systematic one described by this matrix and non-systematic described by this matrix, are called equivalent codes. In this table we have all code words for information words, in this column systematic code and in this column non-systematic code. As can be seen, systematic and non-systematic codes have the same set of code words, however arranged in different order. Assignment of a code word to the given information word is different for both codes. That's the only difference. The set of code words is exactly the same. Parity-check matrix. Let me repeat. Operations of the channel encoder is determination of code words for the given information word, determination of check bits. And this can be done by means of parity-check matrix. An NK linear code can be uniquely defined by the system of M linear equations that express parity-check bits, M parity-check bits, by the information bits. It is normally assumed that the weight of each code word is even, such that the code is called even parity-check code. Just simply parity-check matrix or parity-check code. These terms will be used further on. Parity-check matrix can be introduced. This matrix contains as many rows as we have parity-check bits and n columns, and from each row we may calculate one parity-check bit. So we may express this information contained in this matrix by equations. By equations or in matrix form, these equations are presented here. Parity-check matrix multiplied by a code word transposed code word vector, column vector, is 0. For systematic code, at the left side of a code word we have information word and parity-check bits are at the right. Then it is easy to say that P1 is designated by these bits, PM is designated by these bits, and we may then formulate parity-check sums, like here. Each parity-check bit is expressed by information bits and components of the parity-check matrix. These are called parity-check sums. For non-systematic code, it is normally assumed that all M check bits are also determined solely by information bits. In each parity-check equation, only one check bit is present. And this means that columns of H that are in check bit positions should contain only one non-zero entry. That way, check bits can be designated directly from information bits, and there is no need to solve a system of equations. If we have a systematic code, then it is easy to prove. I'm not going to discuss this slide in details. It is easy to prove that from generator matrix it is easy to find the parity-check matrix and vice versa. So these two descriptions are equivalent. Sometimes we are using generator matrix for some codes. For some other codes, use of parity-check matrix is more reasonable. For example, this is a generator matrix of a code already considered, and this is a parity-check matrix for this code. So this part is parity matrix of G transposed gives this part of H. Syndrome-based decoding. Let me repeat that This is true. Matrix H multiplied by a code word transposed code word column vector is 0. Then, if the received word belongs to the set of code words, then multiplied by transposed and multiplied by H gives 0 as well. If not, then we have erroneous transmission. And this vector, column vector, is called a syndrome. This vector is called a syndrome. It consists of m bits. These bits are calculated from parity-check bits for the given received sequence, and the parity-check matrix is easy to calculate bits of the syndrome. And information relating to an error added to a code word is contained in this syndrome, error syndrome. Then error detection and correction decoding strategies can be updated. These strategies presented before. Error correction decoding. So we calculate the syndrome. We calculate the syndrome for each error pattern. We calculate the syndrome. Then if syndrome is 0 for the received word, we set v star w star equal v. If syndrome is different than 0, it means that we have an error, and then it is possible to find a corresponding error pattern. How? It will be explained later on. Two approaches: syndrome error pattern lookup table, or straightforward like for humming codes. This is example, same code, and let me assume 5 transmissions, 5 words at the output. This word, okay, calculated syndrome 0, 0, which means it is no error, and the decision is that the output of the decoder is same as the received sequence. Same here. For this received word, the syndrome is non-zero, so if we have only detection question mark, we may go further on and try to correct. We are looking on columns of matrix H, and we can see that in 2 columns we have this syndrome, which means that it is impossible to distinguish whether it is error on the 3rd or 5th bit. And then correction is not unique. For this case, here we have the same story, because we have syndrome 1, 0 in 2 columns, so the unique correction is impossible. For this received word, we have a syndrome 1, 1, which is only in column 2, which means that we have an error in column 2. Columns of matrix H are syndromes of V, and syndrome points out an error pattern. If the same syndrome is in 2 or more columns, then unique correction is impossible, like in these cases that we have here, 1 and 2. To correct every single error, obviously all columns must be distinct, all columns of matrix H, not like here, and the syndrome position points the erroneous bit. Okay, that's all.